We currently have a team working on reasoning and planning with reinforcement learning. Sorry, with the large language models. So today I'm going to talk about towards a unified
I
framework
don't know how to do that. That's the thing.
view and symbolic decision making.
Yes.
Sorry, any questions?
You can go ahead, It's the always on our side.
Okay, cool. Yeah, so people know that language model has been used in many different scenarios, right? So conversational AI generations and AI agent, etc. Recently, people also interested in like applying language models for reasoning and planning. So this is actually the focus of our team
Oh
project.
yeah, maybe you can
Hmm? Hello?
you can continue, You can continue.
Okay. Yeah, so
Is it
for these
better?
directions, one thing that's interesting is that you can use the language model to do reasoning planning, but usually they are not doing very well in many different scenarios. So one example is the example called travel planning. So we actually have a paper in this year's ICMR 2024, which is a spotlight. The paper basically show you that for this task like travel planning, the current language model cannot do very well. So the travel planning is one example. Like you have a user that give you some suggestions, right? So basically some requests. I want to travel to some different places with the budget constraint and also with some other constraint in the travel planning. So in order to achieve that using language model, you first like ask the model to do retrieval of different information. Basically, this is a tool use call. So we actually have a database that you can get a lot of information from database, and then give all this information, you basically want the language model to do planning. Planning hopefully can give you a delivery a plan that can actually execute over time. But interestingly, for this kind of task, it's actually uh, really non-trivial to get a language model to work
Better.
well in these scenarios. So we actually did some experiments with our collected data set. So one thing that you actually can find that is that if you use GPT-4 Turbo at that time, it was the best model we can get so far. It actually give you preload performance, right? So the overall pass rate is only like 0.6% accuracy. So 0 to 6%, so which means that for every 1,000 examples, you only have six instances that large model are able to give you the actual trajectories that pass all the checks, all the criteria. So even if you allow the language model to have access to the ground truth results of the tool, then you ask the model to plan and travel, you actually see a performance that is slightly better, but still pretty slow, pretty low, right? So it's basically 4.4% of accuracy. So this basically shows that it's actually very hard to get this model, such model working very well for this complicated travel planning problems, right? So people will wonder, oh, how about O1? O1 may give you some magic, right? So, but unfortunately, we actually retest the O1 results in the same data sets. So what happened here is that even with O1 mini and O1 preview for this complicated task, you can still see that the performance of the final pass really is also pretty low. It's not too much gain. You get a little bit gain there, but the gain is not substantial. Sometimes not even higher than the gain if you do fine tuning. Like so, for example, you have the GPT-4o SFT model that is doing a little bit better. So, and this is basically a phenomenon that is not only on the trial planning task, but also from other tasks as well, right? So on the left, there's actually a paper. This is from Google. This paper is called Natural Plan. It comes with some tasks for the planning, and the existing model still cannot do reasonably well on these tasks. Right. So we have so in this paper, I think the Gemini team really want to promote their work. So you see that their Gemini approach is doing better for this planning task. But there's a worrying trend. The trend is that if you have more variables to be decided for these problems, then all the model performance will drop substantially over time. Right. So that's actually in some sense worrying. So on the right, you actually see this is research from OSU, from ASU, the Arizona State University. You see that O1 and also O1 Proof and O1 Mini, they are doing very well for small scale planning problems, much better than existing approaches. But when you have more and more complicated plans, you actually see that percentage of correct rate drops substantially to 0. Right, so this is something that's really showing that the current models may be able to solve like small scale planning problems, but may not be doing very well in the large scale problems that people often encountered during their study. So the question is, of course, like what is the solutions? Is there any interesting solution you can actually apply to make the problem better? So there are several options I will go to cover in today's talk. Right, so the started one is of course like the scaling loss. Right, people say, yeah, how about we just put more data, more compute, large models, and hopefully the model can do better. Right, so it's very expensive for sure. Another question people may ask is that, does that really work for reasoning and planning? Right, so even with a lot of data, you can still see this kind of a worrying curve with a more complicated planning tasks. The performance actually drops substantially. The second option is the options that I want to mention is the hybrid systems. So we know that we can use solvers to solve this kind of planning problems very efficiently, right? So then how about we combine the deep models and the solver together in different scenarios to address these problems? That's like a way to marrying symbolic solvers and the neural networks. But there are multiple different ways of doing that. Let's first discuss about the first approaches, right? So we can use solvers as a tool use for deep models. So for these directions, we are still sticking with the travel planning directions. So instead of like ask select model to do everything end to end to convert directly from the user request all the way to the optimal itinerary, which is not easy. What we do here is we first turn the user request into a JSON file, which consists like a multiple a line of key informations. And we give him this JSON file as well as a flight and hotel information. You can actually call mixed integer linear programming, MILP, mixed solver, to solve this combinatorial optimization problems. And this will give you a symbolic description of the optimal itinerary. So this is the one. And once we have that, then you can convert this back to a natural language description. And then this will give you a very concrete and detailed and also executable plan given the user request. Right, so that's actually a very simple way of doing that. So for this paper, now this paper has been accepted in ENLP demo session as an oral. And for this paper, we can actually construct the data by first like generating a many different symbolic representation of the user request. Right, so and then you can convert this representation to the natural language. So this conversion is much easier than the inverse order. Right, so we can once we convert this data set, then we can train another model or fine tune another model to start with the user request and convert that back to the JSON files. That's how we actually do this trainings. Yeah, of course, like this MIP solver is in some sense a separate component, right? So we don't train the entire system end to end. But right now it's still working really well. So we actually built a demo for these rough results, and then we also show that doing a human study, we actually get very positive score compared to the baseline systems. When the human is asked to answer the question about whether the system can fully satisfy the request, or whether the system offer a good value of the money, or whether the system is efficient, we actually got pretty positive response. On the other hand, the demo itself is actually pretty quick and fast, right? So you can see that the breakdown of the time and the performance is actually really good. It actually will recover like 80 or 90% of the constraint. At the same time, the speed is very close to real time. right? So it takes 2 seconds to construct the instructions from the natural language, to the JSON files. And it may only take a half a minute to call the solver to give us solutions, even with like, for example, multi-day trip with complicated constraints. Right, so that's like a one way to do this kind of hybrid systems. And
I have a quick
yeah,
question. So
yeah.
when you apply the solver, are you using that to refine the result from the large language models, or?
No, there's no refinement. When we apply the solver, we just use the JSON file as the input. So basically, there's no solutions provided by the LLMs, right? We just ask LLM to do translation, to translate from the user request all the way to the JSON file.
I see. I see.
And JSON file is a specification of the optimization problem. Yeah.
So in the sense that this is using large language models to formalize the problem into something that a solver understands, right?
Yes, exactly. Yeah, you can see
Okay.
that.
Okay. Okay. Thanks.
Yeah. And this seems to be a workable system we can use. Of course, like a follow-up would be things like in the previous work, we basically do a one-shot translation from the natural language request all the way to the JSON. But in the next step, obviously, you want an agent that can talk with the traveler in this kind of chat form to progressively collect information from the travelers. Right, this will be very useful for the travelers because the traveler does not have an idea about what matter the most to them. And in many cases, like a traveler may also omit many details in their request. So by proactively asking multiple questions from the travelers, the agent is able to collect enough information and call the solvers. Right, so that's actually a follow-up of this work, right? So this is called APEC travel agent that achieve a higher performance in terms of multiple criteria for the agentic behaviors. So this is actually a paper that we're going to put to archive very soon. And for the paper, what we do here is that we actually generate lots of synthetic dialogues from the Llama 3 for 5B model, and use that data to train our models using SFT and also using iterative improvements. Yeah, so I don't want to talk too much about the paper because it has been put on the archive yet, but I think you're going to check the paper in details once it's put on the archive. Yeah. Okay, so that basically concludes the first part of the systems. The second part of the system is in some sense a different order, right? So on the other hand, maybe it's possible to provide a lot of data from the solvers to the deep models, so the deep model can give a much better performance, right? So this is another way to leverage the solvers. For this kind of thread, we actually have a bunch of work that seems to be interesting, and then I want to introduce in this talk. Right, so this is basically like a paper that we want to leverage solver informations. Right, so the paper is called Search Former. In this Search Former paper, what do we do here is that basically like you have a prompt to introduce basically the environment, introduce the problem settings, right? So here the problem is to navigate the maze, right? So you start from a starting point and you find what is the shortest path from the starting point all the way to the goal. And so for this one, of course, like if you don't have any knowledge about neural networks, what you can do is that you can call a star search or some breadth first search or deep first approach to search the graph and find what is the shortest path from the starting point all the way to the ending point, right? So traditional transform-based approach was think about, oh, how about we just take the problem description as the input and then predict like the actual plan, which is the optimal path. But here, what we do is like we actually also incorporate the search trace of the A star search into the predictions, right? So all these lines in purple and also in teal, these lines are actually intermediate results from A star search, right? So usually in A star search, if you know the details, you will actually see that the A star search will intuitively create new nodes and explore along different directions, and also closed nodes that has been iterated, has been explored, right? So an A star search will also maintain a heuristic function, maintain like a table that basically save like all the current like frontiers of the search, and then using a heuristic value to decide where to go, depend on how much the progress it is. So in our search framework, what we do is like we put all these traces together into the decoder sequence before we actually decode the final optimal plan. Then we actually have two models, right? So the first model is called solution models. What it does is like it's very similar to all the previous approaches, right? So when the prompt is sent to the encoder actually gives you a representation. And then the representation is driving the decoder to directly output the plan. But on the other hand, the search augmented model, basically you still have an encoder to encode a prompt into a vector, and the decoder actually first generate a trace and then generate a plan. So that's actually the difference between this search augmented model and the search only models. Right. So, but surprisingly, with this simple approach, you actually see very different scaling laws. Right. So for solution only models, what you see is kind of like a regular scaling law curve. Right. So with more and more training samples, the performance is obviously going up, but it's going up pretty slowly. Right. So with 1 million training samples, then you get like a very close to 100% accuracy. But with only 15 samples, 50K, you get like a very low accuracies. However, if you check the search augmented models, then what happened is that such models has a much fewer number of parameters, right? So it's 15 million parameters versus 175 million parameters. And at the same time, this search augmented model has much better performance, even with a much fewer number of training sequences, right? So this is in some sense very interesting because in this case, like it has the search augmented model has a much more much fewer parameters and is much more data efficient. Right, so this is same thing happens for this task called Sokoban, which is a little bit more complicated and requires a lot of plannings. Right, so in this task, what it does is that you have one agent that you want to push these boxes into their destinations. You can only push, but you cannot pull from a dead end. And in that cases, you see that the search algorithm model will also give you better performance in the same number of parameters. So far we actually see there's an interesting new scaling laws if you add the server's trace to train the transformer with teacher forcing. Given that, I mean, of course, like we can do better because the final search augmented models is already differentiable and can be readily improved further if we have new signals. Then we can actually fine-tune these search augmented models to achieve shorter trace, but still leads to optimal plan. Right. So you ask this search augmented model to generate lots of trajectories, and you pick the trajectories that has a fewer number of steps in the its own like a search trace, but you still end up with the optimal plan. Right. So you pick this subset of the data, and you fine tune your model on top of this data, and you can do this iteratively. And this basically gives you a search former results. And this search form model actually doing quite well in many different scenarios, right? So for example, for this Sokoban task, first you can always construct a search augmented model following the traces given by A star. And you see the distribution are actually pretty similar to each other. And the x-axis is the distribution over the trace length distribution over different outcomes which are optimal. Right. So, but after you do these iterations multiple times, what you see is that the length of the search trace, while still giving the optimal, this statistic actually has a shifts towards the left, right? So, which means that the average length of the search former is shorter than the search trace of A star. So, that's why we call this paper beyond A star. In terms of numerical numbers, you actually see that we the search former results actually achieving higher scores compared to the existing approaches. Right. So here, like we actually define a metric called the improved lens ratio. And this is basically like related to the ratio between the optimal the A star search trace and the current search trace provided by the models. So if the lens ratio is higher, then this means that our improved search trace becomes shorter. Right, so that's why the number become higher. So you see that the number actually become higher over time when we have more and more steps in the search format, which is very nice. And at the same time, surprisingly, the optimality rate for the search form output is also getting up. Right, so this is something quite surprising because that's not part of our objective. But interestingly, it also happens when the search length becomes shorter. Right, so basically you see that the optimality started from 86% for solution only to 90%-ish for search augmented, which means that the search augmented model is already improving on top of solution only. And then it become even higher after a few steps of the search formats. Yeah, which is actually very interesting. And this is actually comparable with search only solution only models, which much more number of parameters. Right. And recently, we also have a follow-up for this paper that's called dual former. It's a version 2 of the search former. So in this paper, what we actually find is something really interesting and exciting. So also the motivation of dual former is to reduce the length of the search trace during the training. Because usually like the search trace can be quite long. Right? So this is actually pretty efficient. But when we actually reduce the length of the search trace by dropping some of the search trace details, and also adding the search only, solution only data during the training, we actually find something very interesting. So the resulting model will automatically switch between fast mode and slow mode at the same time. So that's actually a very interesting experiment and results. At the same time, and this final model is actually better than either the search only models or the solution only models. Right, so this is a very interesting results. So we all know that usually people talk about system one and system two kind of approaches, right? So and the people usually will think, oh, maybe these two system one and system two, they are separate systems in usually like maybe human's brain. And then you have to switch between two and one and two, and sometimes you just distill from system two to system one. But now this paper actually shows that if you have the right mixture of the data, then all of a sudden you can have a system that will automatically switch between these two modes at the same time. Right? Sometimes it will give you a fast mode by directly outputting the outcome. Sometimes it will give you slow mode by first thinking through the search process and then giving you the outcome of the final plan. Right. So, and you can actually have a model that can do both and better than either of the directions. So here, the controlation of the system one or system two thinking is just by a single token, right? So for the dual former, what we do is like if we just let the dual former to generate the next token and next token, and it actually in this auto mode. In auto mode, the model will automatically decide whether it goes to system one or system two. But you can also ask the model to focus on system one or system two manually by specifying the first token it is generated, right? So if the first token is something like a plan, then the dual former will get into the fast mode because after the plan token, you actually will directly output the final plan. But if the first token generated by dual former is correct, right? So which is basically the first token for any trajectories, for any like a thinking process or search trace, then the model will get into the slow mode, right? And you actually will see that in both, if you ask the model to do either fast mode or slow mode, then you actually see better performance compared to the complete trace baselines. Right? So and very interestingly, the diversity of the fast mode and slow mode actually become higher. So this is very important because this will actually improve the test of the compute scaling laws. So uh, if you have like a more diverse output, then of course the final outcome is more likely to be true for at least one of it. Right? So the test of time diversity and test of time compute efficiency will be higher. This is something that can be achieved by just manipulating data distribution. We also apply the same idea to math problems. Right? So in the math problems, what we do here is that we also can start with the existing chain of thoughts. Right? So it's actually augmented version of the chain of thoughts. We can actually randomly dropping some of the passes, right? Some of the intermediate steps, and then you use that data to train models. It turned out that the final outcome of the dual former in these cases is actually shorter in terms of the COT length. In the same time, the performance is actually also better by maybe a few percent, right? So here you can see like there's a performance in Mistral 7B and also Llama 3AB. So what we see here is that data set called mass, it actually had a performance in two different scenarios. One is like greedy decoding, and the other is the pass at 20. Right, so these are pretty low number, but if you do augmentation of the chain of thoughts, it actually give you better performance. That's something that people already found in the previous papers. But in our case, we actually try to do a random dropping of the traces, path of the traces. So what you see here is that it actually even give you even better performance. So it give you like, for example, 1% boost in terms of the greedy at 1, and probably like a 2% growth in this pass and 20. At the same time, the trace length is also shorter than the original Argmax baselines. That is very interesting to see. And finally, you can actually compare the dual formula with OM preview. Of course, this is not a fair comparison, but at least it shows that our approaches is doing very well for the specific task. But Owen, for this specific task, failed to actually understand the problem at all, and will have an invalid path to go from starting point all the way to the ending point in the mass navigation. Okay, so here I conclude the second part, and then I will proceed with the third part in option 2. Do you have questions?
Yes, please.
Yeah.
I really like this part of the. I was wondering, like, so there are different levers with LLMs. We know, like, we could fine tune, we could like pass it everything in the prompt with many in context learning with long context. So I was wondering if we consider passing the search traces, let's say in the prompt, what
I
advantages,
see.
disadvantages you think? Uh,
Yeah, I think this is a good question. We haven't tried that systematically yet,
right.
right? So initial trial is doesn't seem to be working very well. But I think I agree that there need to be systematic trial to see whether this will work or not. Yeah.
Okay. Mhm.
And because usually it's pretty long, right? So, but by the time that we started the project, there's no many very long model with super long context. But I think right now the technique of long context now become much more mature. So maybe it's time to try something like that. Yeah.
Right.
Yeah.
And I'm also curious to know your general experience working with these models, Yuandong. Compared to pre-training or post-training, where do you think we get the most leverage in terms of reasoning and like planning capabilities? Like spending, like we could add more data during pre-training, or we could do this test time scaling, maybe. So which one do you think generally?
I see. So usually you still need some fine tuning at least to get good reasoning powers, right? So pre-training usually just means that you have to cover all the informations to learn the representations.
Right.
And for reasoning, you actually have two dimensions. Dimension one is that where the model can actually follow the attention references very well, right? So then you can actually do the reasonings. So that's one thing. So this sometimes like you can achieve that by full post training. And there's another part of reasoning, which actually I will mention later, is that what kind of representation you will learn from existing reasoning tasks. With good representation, of course, the efficiency will be much higher. So for that one, I'm not sure it can be learned from post training. I'm actually not sure. Yeah. So there's two different representation, two different aspects of reasoning. Right?
Yeah. Thank you. Yeah. Thanks a lot. Yeah.
Okay. Yeah. Cool. Any other questions? If no, then we can proceed with the second, the final part of the option 2. Right. So there's another approach that we can do is the deep model plus solvers. So this is actually the circle paper that I think Aaron mentioned in the beginning of this talk. So in that paper, what we do is a kind of separate problem. It's not related to large models, but hopefully we can incorporate that into large model later. Right. So in this case problems, like we want to address the nonlinear objectives with combinatorial constraints. Right. So in that kind of problems, we cannot call existing solvers because existing solvers can only deal with linear constraints. That is pretty restrictive. But on the other hand, real-world problems actually have a lot of non-linearities. Right. So for example, you have a computer systems that has a lot of nonlinearities across these coupling terms. But in that case, is how we still leverage solvers at the same time, scaling like good solutions. That's a big problem. So here's one example. So this is actually example we actually encountered in the production when we are trying to discuss with the production team to see whether we can do anything about it. So in these cases, what happened is that you have K tables and you have N identity devices. These devices basically mean GPUs. And you want to put these K embedding tables into these devices so that each table will require, each device will hold as many tables as possible, but still within the limit of the memory capacities. And at the same time, you want to minimize latency, which is actually estimated by a neural network. Right, so that's basically the problem. And then you can formulate the problem in the following sense. Right, so you have a minimization problem, minimizing latency, subject to these constraints. Right, so here the xij is kind of a binary variable. By sending the table I to device j. Of course, like each table need to be placed to at least one device. Now that's why you have this constraint. And at the same time, for each device j, all the summation of all the tables put onto it has to be following the memory capability, the capacity constraints. So this is a very typical formulation that we can encounter. Error is very nonlinear because this is the misuse, right? So because of bad chains, communications, etc. So you have all these issues. You cannot call solvers directly because error is nonlinear and you have no idea what it is. But what we can do here is that we actually can map everything to latent space. And then in this latent space, we actually want to solve a surrogate optimization problem. So that the surrogate optimization problem will give you a solution that directly optimize original nonlinear functions as much as possible, right? So in other words, what we do here is that while this original space has nonlinear optimization problems that is very hard to solve, what we can do is that we try to predict a surrogate cost so that for this surrogate cost, it will give you a linear optimization problems that are subject to the same combinatorial constraints. And the final solution will optimize the original nonlinear problems as much as possible. So people may wonder, like, okay, this sounds like a kind of convoluted ideas. How can we optimize everything together? The answer is very simple. We just use gradient-based optimization. So what we do here is that you have some surrogate coefficients here, C coming to the solver, and the solver will give you a solution, and the solution will put into the objective. The objective will give a loss. Right? So you have this computational graph like that. but you can actually do backpropagation for this computational graph. Right, so objective functions, while it's nonlinear and non-convex, you assume it's a differentiable, then you can backpropagate. And the solver itself can also be backpropagated so that you actually get a gradient for the surrogate coefficient C. Right, so then by doing backpropagation all the way end to end, you are able to find what is the best surrogate cost C that can optimize the problem. Right, so by doing that, you actually have end-to-end system that also incorporate the solver and at the same time can solve the entire combinatorial problems, even with nonlinear objectives. So we actually try these ideas in many different scenarios. So one is the embedding table sharding, right? So we actually compare this with existing benchmarks. So we compare this with domain heuristics and also greedy approaches and also the reinforcement learning-based baseline called the dream shard. So there's two metrics. I mean, the first metric is, of course, the latency of the overall solutions, which is the loss of the objective function. And the second is the runtime of the deployment, right? So you really want the system to act quickly. So you actually see that our circle and its variant, there are three variants, circle zero, circle prior, and also circle hybrid. And the circle prior is basically to say that you want to predict the C, but the C is also a function of the problem descriptions. So then you actually have a second, the additional parts of the gradient descent and to be optimized. And once you have this second part of the gradient descent optimized, you can directly predict the cost values from the description of the problems, right? So so this is actually giving you faster results compared to the circle zero, and at the same time, the solution loss is actually reasonably good compared to existing baselines. So we also can apply these ideas to an inverse photonic design, which is also a production use case. In that case, you actually have an 18 by 80 grid, right? So and you want to put 0 and 1s, which is whether you have materials or not, onto the plate, so that this entire thing can bend the light, shooting from the top to different branches, depending on their wavelengths. Right, so in order to compute the optimization function, it is very complicated. You need to basically solve electromagnetic simulator. And at the same time, once you have a simulator, then you actually find the frequency response, and then you get the loss functions. So it's super complicated. But the solution space is actually binary, right? So and also it will be constrained by linear constraints. The linear constraint basically shows that the solution has to be feasible by the manufacturer constraint, right? So either you put a dots with kind of minimal size there, or you don't put anything at all. So there's some kind of linear constraint that you are associated with that. And we actually run this multiple tasks in this design problems. And what you see here is that our approach is actually give you a much smoother convergence curve towards the zero, which is the satisfactory compared to the existing approaches like pass-through rate. Right, so this is in some sense showing that the power of these combined approaches. Yeah, there's some limitation of the circle because you need to deal with the gradient descent, right? And also you need to make sure that circle is differentiable. We actually have follow-up works called Lancer and Genko that try to address these problems. But for the limitation of time, we won't be able to capture that. Okay, any questions here?
Yeah, no, so when you do this, I suppose it's end-to-end training, right?
Yeah.
So how do you generate the training set?
Oh, it's very simple, right? So for the training set, what we do is that we actually create many problems, right? So we create many problems. So and for each problem, so for example, you have lots of problem description, yi. Each problem description, they define objective function. Right, so each problem, so as long as you have a bunch of solution yi, so bunch of problem description yi, you can generate as training set, and you can train this entire thing on the training set. So once this get trained, then you automatically will learn this surrogate cost prediction. Right, so and this surrogate
So
can be used
right,
for
but I mean,
problems.
I mean, I suppose that this probably cannot scale up to, very large search space, right? How many variables do you actually have, the discrete variables?
Oh, so for example, for this kind of inverse photonic problems, this one is like, for example, you have 18 by 18 grid, then you have 1.6K binary variables.
I see.
So basically, like, I don't think there's some scaling in terms of the solvers, because the solver usually can address pretty large problems, right? Large scale problems. You might have thousands of variables, and the solver can still handle that. So that's okay.
Right. Okay. Yeah, I think that's the limit of the current mixed integer solvers. Another question is that the idea here seems a lot like the Frank-Wolf kind of idea, right? Frank-Wolf kind of idea, each time they linearize the objective and they, solve a feasibility problem. I mean, they keep the original constraints. Have you guys tried to benchmark against that?
Yeah, I think for the linearized approach, first of all, I don't think this approach is a linearized approach, because it is possible that you actually don't do a Taylor expansion of F, right? So what we do is you directly find some surrogate cost, which may not be the Taylor expansion of F, and it has nothing to do with that.
That's right. That's right. But I mean, I'm because Frankfurt kind of idea is also taking a linear model. Of course, they'll produce different linear model to the
Yeah,
original.
yeah.
I'm just saying, have you guys tried to benchmark against that kind of idea? I mean, Frankfurt kind of idea.
Yeah, I think we haven't done that yet. Yeah. So if necessary, we should do that.
Okay. Thank you.
Yeah, I really like this line of work, Yuandong. I mean, I worked on constraints earlier. Handling at
Okay.
that scale is always tricky. I wonder, I was curious, like, so this is the end-to-end approach, but looking at the part one, the analog of that here would be like some model-based optimization, like Bayesian optimization or reinforcement learning. What pros, cons you see compared to that? I'm curious to know.
Yeah, so we indeed have some comparison with kind of black box approaches, right? So I mean, for example, like genetic algorithms, but they are not able to do very well in the training, in
Right.
solving, because usually for genetic algorithms, they claim to solve everything, but usually it may take days to even find a feasible solution, right? So because there's no efficient way to model the combinatorial constraints in the genetic framework, right? So, but because these approaches are well formulated by mathematical programming, then I think the mixed engineer programming is much more efficient with that.
Right. Just trying to distill down some first principles from this approach. So the real benefit here is that because of the gradient-based optimization, we can include the solver in the neural network, and just the capacity of the neural network to handle that is the first principle. Is that right?
Yeah. So because things can train end to end, so basically the neural network will find a way
Right.
to assign the solver the appropriate weights, so
Right.
that the solver will give you the solution to original nonlinear problems. Right.
Right.
So if you already have 1,000 some such examples for
Right.
the stable distribution, then of course you can put them into the training, and then hopefully the neural network will figure out the mapping by itself.
Right. Okay. Okay. Yeah. Thanks.
Okay, cool. Any other questions? Okay.
Hi.
Yeah.
I have a question here. Yeah. I'm wondering, for the photonic design problem, do you have any restriction for the solver you use, or that is any solver can be used for your model?
Yeah, I think so. Any solver can be used in the model. So this framework has nothing to do with which solver you want to use, right? So here is independent of solver. So basically, you can use any kind of solvers, right? So you might use CVX PY layers. You can use CVX, right? You can also use Skip or Gnubi, whatever. As long as you find a way to differentiate to compute a gradient from the solver solution back to the coefficients. You can use solver. So basically, this approach is independent of solvers.
Yeah. I'm asking because for this electromagnetic simulation, actually, in engineering, we usually use a component from ANSYS. It's like a finite element based solver.
Oh, I see. Okay.
Yeah, but usually for that one, it cannot be directly integrated with this differential programming. I just wondering how. Do you have any idea?
I see. I mean, you can always do some kind of numerical approaches to compute gradient, right? So here, conceptually, the solver need to be integrated into the system. But empirically, what happens is that you only need to get a gradient from the solvers, right? So the solver takes some input and give you a solution. But what you really care is that you want the solver to give you the backpropagated gradient as well when there's a gradient that's backpropagated from the solver solution. That's it. So once you can compute,
I see.
you can compute the gradient, you can use this approach.
I see. So as long as you can get the gradient, no matter the differentiable or numerical based gradient, that will work for your
Yeah. So that's pretty much it. And also we actually have follow-up. So this is the landscape. So there's a landscape surrogate paper. So in that paper, what we do here is that you are actually using a neural network to simulate the solving process during the optimization, right? Because solving usually is very slow. But if you have already get a lot of solvers results given their input, then of course you can learn some surrogate cost to simulate the solver behavior. And that simulate neural network can actually get the backpropagation gradient very naturally, right? Yeah, so this will actually improve the speed of the training process.
Okay, thank you.
Yeah, I didn't mention that, but if you want, you can definitely read the paper, and it has nice applications there. Okay, that's okay. Then I have 10 minutes for the option 3, which is something that I'm really excited about recently. So the option 3 is that okay, maybe actually there's actually an interesting structure in the neural networks, right? So the neural networks may actually convert to something symbolic. So this is in some sense like a more detailed or deep understanding of how the deep model works. And if the deep model can actually have emerging symbolic structures, then this symbolic structure may support unification of the previous symbolic approaches and the neural network approaches from the first principles. There's something that happens really in some of these reasoning tasks. So for this kind of topics, I mean, of course, there's a debate between the language models, whether the language model can really do reasoning or it's just doing retrievals. So on one hand, I mean, some people who are believing in scaling laws, they really like language models because it actually show emergent behaviors, right? So here's like a very nice GIF files from some blog post that I shamelessly steal. So you actually see that it's a very nice GIF animation showing that with more and more parameters, and you have so many capabilities emerges from that. So, but on the other hand, we actually see very different opinions, right? We saw opinions like AM is just doing retrievals, right? So we don't really believe in this reasoning powers, and this reasoning power is actually very fragile and may actually breaks very easily in different scenarios, right? So, for example, recently there's a paper from Apple that construct this GSM-AK symbolic. And in this paper, what they show is very interesting. So they actually add some irrelevant sentences in the GSM-AK dataset. These sentences should not interfere with the normal reasoning chain. But interestingly, all these models, they basically get confused by this particular sentence. And it gives you a lot of degradations in terms of performance. The accuracy drop is crazy. Right, so then people may just ask, okay, maybe RM doesn't really understand what is reasoning, it just do retrievals. rather than reasoning. So in order to clarify this kind of problems, it's a very hard problem. One thing we can think about is that we can start from this very concrete example, which is called the modular addition. This example is in some sense quite simple, but at the same time very interesting because it actually has very nice, interesting structures there. So the model addition problem is super intuitive. Right? So you have two numbers, A and B, and you compute A plus B, but mode some large prime number D, right? So this is a very simple task, and you can imagine that you can just put everything into a table of size D by D. Then once you have the table, you solve the problem easily. Yeah. So that's pretty much it. But then you may naturally think about, yeah, maybe the neural network have an implicit table to do retrievals, right? So maybe like you can actually will expect that neural network will give you some tables to learn to retrieve. But interestingly, if you actually train the models, what you see is that you actually learn a Fourier basis to represent this model addition task. And this has been perceived by previous examples, right? So for example, in the previous settings, what you see that you actually see different frequency of these tasks, different frequency of this task of these numbers represented in the embedding space. So then the question is, of course, why? So why you need a Fourier basis for this representation, and how this representation is connected with the symbolic settings. So for this, we want to basically like try to address this problem with the minimum but viable settings, right? So we consider this two-layer network, bottom layer and top layer. And the bottom layer takes one hot representation of A and B into the neural network weights, and they are going through Q hidden nodes, and each of them has a quadratic activations. And then send to the top layer, and top layer output something. And you want to minimize the loss between the output and the one hot representation of C. Right, so very simple problem setup. And if you execute and you basically like do a gradient descent, you actually will see Fourier basis emerges from the training. So in order to do analysis, we first do a Fourier transform for all these weights. And because all these weights are real, and there need to be a Hermitian conditions holds for all these Fourier bases. And but what we see from the gradient descent solution is super interesting. So here's a figure that's showing the results of the gradient descent solutions. So here the x-axis is a hidden index, a hidden node index. So here you have a q equals 20, which is kind of 20 hidden nodes. And for each hidden nodes correspond to one index from 0 to 19. And the y-axis is the frequency of the after Fourier transform. So you actually see like a very clear patterns for the final solutions, right? So in particular, for every frequency, you actually see exact 6 neurons that has a non-zero Fourier transform along the line, right? So for example, for the frequency 1, you have 1, 2, 3, 4, 5, 6. You have 6 neurons. And for frequency 2, you also have 1, 2, 3, 4, 5, 6. So these are all the 6 solutions. So that's actually quite interesting. You also see that other solutions, right? So for example, in this particular case, you see frequency 2 has 4 solutions, has 4 neurons associated with that. Do I have 1, 2, 3, 4, or the 4? But at the same time, you also have some bias along other like neurons, right? So it's highly regular. And you may wonder like, okay, whether this happens for like a more larger scale problems. The answer yes. Right. So this is an example for d equals to 23. Right. So you actually now we actually do distributions. Right. So you basically compute distribution of the solution orders at all frequencies. So what happens is that the order for all the solution really happens, and you actually see 2 sharply peaked solutions at 4 and 6. Right. So, and if you scale the problem even more, I mean, for example, if you scaled up to d equals 127, you actually will see these two peaks at the same time. But there's some kind of weight decay need to apply. And with very strong weight decay, obviously we'll see all the solutions collapse into solution zero, which means that everything is zero and you don't get anything. But other than that, you actually see these two peaks very clearly emerges from the training. Of course, like people will ask why that's the case. It's very regular. It's interesting that there's actually a very nice algebraic structure and interpretation from that. You can start from the structure of the loss functions, right? So since we are doing MSE loss, so what happens is that you can actually expand MSE loss into this kind of complicated form, but actually very useful form. So this MSE loss has two structures, right? So it has some negative terms plus sum of squares. There are three sum of squares there, and also there's a term that is you want to minimize the cost, right? So these terms is basically this kind of polynomial terms. And you might wonder like why you want this to define these terms, which seem to be very complicated. And I think the reason why the term need to be defined this way will be shown later, very soon. So one symmetric condition of this solution, global optimal solution, will be you put all this sum of square to be zero, right? So you have everything zero here, and you want the first leading term to be one. So this is the minimum possible number you can achieve, right? So the symmetric conditions. But with this symmetric condition, people wonder, okay, it's very complicated. How can we find the optimal solution given the symmetric condition? While it's nonlinear, there's some nice algebraic structure that can enable us to do that. So first of all, if you think about all the two-layer networks with different number of hidden nodes, so you think about these networks and put all these weights together into this large space, Z, and you can show that this space will follow a nice algebraic structure called semi-ring structures. So with definition of ring addition or multiplications. So ring addition is very simple by concatenating hidden neurons together. The ring multiplication is basically done by a chronic product along the hidden dimensions. In that case, this structure will become a semi-ring. And moreover, the two terms that you actually shown previously in the loss functions, they are actually the ring isomorphism, the homomorphisms for the semi-ring structures. So then what does that mean is that you can actually start with partial solutions that only satisfy one or two constraints. So here, like you have partial solution of 0, 1, satisfy this first constraint being 0. You can also construct another partial constraint Z2 that satisfy another another term being 0. Then, because of the property of the ring homomorphism, you can multiply these two solutions together with the ring modification. Then you give a solution Z, and the solution Z will satisfy both of the constraints simultaneously. Then by using this mechanism, you can basically construct the global solutions from the partial solutions intuitively, right? So you start from partial solutions, and these solutions only satisfy a subset of your global optimal constraint. Then you can compose the solutions using ring modifications to get a better solution. And then you construct solutions with the ring addition, and finally you achieve the global optimizers to the original loss functions. Even if the loss functions are high nonlinear, you can still construct that. So we can actually follow this kind of construction paradigm. You can construct many different solutions. So that's all the 6 solutions you construct by multiplying a solution of order 2 and a solution of order 3. And then sum them together over different frequencies. You can have another order 4 solutions. That is basically like you have a order 2 times order 2 and sum over all the possible frequencies. But it need to be amended by all the 6 solutions. You can also construct solutions that it can do perfect correspond to the perfect memorization, which is all the D solutions. So once you have construct solutions, you can prove that, of course, they are actually global optimal, which is good. But most interesting is that if you actually check this gradient descent solution and the scrutiny, the gradient descent solution is actually follow exactly the construction that we just did in our previous theoretical studies. To see that, we first basically get lots of gradient descent solutions And then we check, first of all, whether the solution are the 4 or 6. Right? So in these particular scenarios, you see that 100% of them are all the 4 or 6. And second, you check whether these all the 4 and all the 6 solutions, they are factorizable into either 2 times 3 or 2 times 2. Right? So this is basically the constructions that we use in our theoretical constructions. It turned out that 95% of such solutions can be factorized this way. And errors are very small, so its error is like a 0 point some percentage, not like a large number, which means that factorization really makes sense. And finally, if you check the factorization component, they are actually precisely match with the theoretical constructed forms, right? So you can actually write them down analytically with different parameterization, and you actually see that most of solutions, they fall into these categories. Only 2% of solution does not match into these categories. But even within 2% of solutions, if you check them one by one, they actually are still the solutions in these forms, but may not converge all the way to the end. So if you actually print out the distribution of the parameters in these solutions, you actually see very nice structures as well, right? So it looks like gradient descent really prefer solutions that will lead to highly symmetric structures, which is a super interesting and something that we haven't fully understand yet. Yeah. So, but public implication of this line of research is that it is possible that, I mean, first of all, it's very surprising that the gradient descent solution actually end up with a solution that is explainable by symbolic systems, right? So maybe one question would be, does the neural network actually end up with learning more efficient symbolic representation that we don't know, right? So now we know something because we construct such algebraic structure. But maybe in the future, for more complicated tasks, you can also construct such structures so that the gradient descent can convert into that, right? So another implication is that maybe gradient descent is just one way to achieve the solutions. There could be other ways to achieve the solutions. For example, if you can use very advanced algebraic operations, maybe it will also give you a solution that is similar to gradient descent. So in that case, maybe you don't need to use gradient descent anymore. Maybe gradient descent will become obsolete eventually. But of course, these are basically speculations. But this paper actually gives some of this dim light, showing that this might be possible for complicated systems like neural networks. So in the future, maybe it's possible that we can start from preying the system to work very well, because there's a black box, and you can open a black box and eventually find a better understanding of the neural network, and can make this entire system working much better. Thanks.
All right, thank you very much, Yuandong. For the sake of time, we probably have time for 1 or 2 questions before we close.
Yep.
Any questions from the classroom? So I do have a question about the final piece, which is very interesting, of course. How sensitive is this phenomenon to the loss you choose? You emphasize the MSE loss.
Yeah.
What if you switch to other loss?
Yeah, that's a very good question. So for other losses, I haven't done very systematic experiments yet, right? So the previous results actually show you can still get Flory bases, but they will be distorted Flory bases, right? So yeah, so you get that. So, and also, of course, the way to factorize the solution may be different. So there's something that we need to figure out. Yeah.
Yeah, because I'm wondering if there's anything special about the MSE loss, because we know that Fourier the energy in the Fourier transform is preserved only under the
MEC loss.
L2 norm, right? So
Yeah,
there's something special about that, right?
Yeah. So I think that's
and also I think your analysis, if I recall correctly, your analysis is basically equivalent to you do a Fourier analysis on a semi-ring, right?
Yeah, actually what happened here is that if you do Fourier analysis you first do Fourier analysis and you can basically do the ring multiplication. So this ring multiplication definition is related to the Flory basis.
Mm-hmm.
Right? So if you do so basically like if you do a canonical product in the Flory basis, this is basically the same as if you do maybe like a more convoluted operations in original basis.
Right.
Yeah.
Right. Yeah, I kind of feel that there may be something special about MAC loss. That's the.
Yeah.
It's
Yeah.
just because it's so special in Fourier analysis in general.
Yeah, it's kind of special because with the MAC loss, you can actually decompose the loss into this form.
Right.
Each
Right.
form will have nice structures there.
Right.
So if you have a softmax, maybe it's different. So it's true. But then the question is like now you have one data points, right, showing this is possible. But in the case, it's possible to expand this data point to more general classes. Yeah, we don't know yet, but this is basically first step.
Any final questions before we close? People online? No?
Thanks a lot for the talk.
All right. Thank you very much again, Yuandong, and thanks everybody for attending the talk. See you
Okay.
next week.
Yeah. Thanks.
Bye-bye.
Yeah. Bye.
Thank you.
Bye.
Thank you.